Hey there, Math 2403. Welcome to your first statistics lecture. In today's video, we're going to start talking about Unit 1. We'll do an introduction to statistics. We'll talk about some sampling procedures, and then we'll look at some graphical summaries. So let's just jump right in. Here we are in Unit 1 Descriptive Statistics. Now, in your Course Learning Hub, you should have a copy of these notes that allow you to follow along. You can make your own notes as you go. In future units, there'll be more space. We'll solve more problems, uh, basically with the fill-in-the-blank template style. But this first one, we have to cover a bunch of definitions and get a bunch of background information. So there isn't a lot to write in this first one. So you can probably just follow along, probably at 1.5 speed, uh, as some of this might seem a little dry. During tests and things, I never ask students to simply give a definition for something, but I will use terms in the questions which would require that you know at least roughly what they are, but you won't need to uh, know exact word for word definitions. You won't have to memorize things like that. So diving into this, what is statistics? Statistics is basically a field of mathematics, and they are actual individual measurements. So we use the term in a few different ways. I opened up a few different stats books and looked for a definition of statistics, and basically I didn't like any of them, but I pasted a few of them together to create this one. Statistics is a collection of methods for planning experiments, obtaining data, organizing, summarizing, presenting your results, analyzing, interpreting, and coming up with conclusions based on the data. So I'd hate to have to spit that one out again, uh, but it does pretty much cover statistics because it is such a broad field. How might we use this in building and architecture? Well, statistics is basically everywhere. You get bombarded by statistics now, particularly on the news. But in building, we could say, sustainability, designing for sustainability. There's a lot of statistical research that goes into that, or green versus traditional designs. If you're doing comparisons, you could do a statistical analysis. Looking at soil concentrations for designing your site, reliability of materials, designing for extremes, that 1 in 500 year flood or the 1 in 100 year earthquake. Material strength, certainly. And then in a manufacturing context, we have producer and consumer risk analysis. We'll basically talk about these sort of applications as we go along. Right now, we're just getting our feet wet with the basics of statistics. The big thing that we need to get right off the bat is the difference between populations and samples. The population is the complete collection of whatever you'd like to study, and a sample is some subset of that. Basically, we would like to study an entire population, but it's too expensive or too difficult to study everyone. So we somehow get a subset of the population and we study those values. Now, we hope that our sample then represents the complete population. This is the main thing that we'll be doing in the course is estimating something about a population, some attribute of a population based on sample data. So if you understand this pretty crude a little diagram, you kind of got the gist of a lot of what we're doing in the course. Obviously, there's a lot that goes into that. What procedure is used to collect the sample? What attributes should we measure of the sample? And then how much error might we have between our sample result and what the actual population value is? So all those things, they'll be coming up. Speaking of populations versus samples, populations, we will have characteristics of those populations, and we'll call those parameters. And then when we're studying samples, we'll have statistics. So we'll have the mean of the whole population or the mean of the sample. When we're talking about the population case, we'll call the mean a population parameter. And when we're talking about the sample case, we'll be talking about statistics. And we'll often use different symbols. For example, I mentioned the mean. If we're talking about the mean, which is, the average, we use a symbol for the whole population. We'll use Greek letters typically for populations, and then we'll use our regular alphabetic characters for samples. I modified this one a little bit. So the mean of a sample is referred to as X bar, and the mean of a population is denoted with the Greek letter M, which is mu. So this is a Greek M, mu. I drew this, the little cloud picture that we had in the previous page, just another way, basically. You have your population of interest, and you need to come up with some plan. How are you going to pick items from this population to come up with your sample? Then once you have your sample, you can basically do descriptive statistics like, summaries and plots and things. And then you can do another branch of statistics, which is inferential statistics, where you actually come up with predictions or decisions, and you weight these predictions and decisions using probability. So we'll basically, in the unit 1, we'll basically be talking about sampling and summarizing, and then in future units, we'll talk about how we might make predictions and decisions that are probability weighted. So we'll have to have a unit on probability before we can really attack that decision-making portion. We already mentioned this, but why would we ever sample over just study the whole population? Well, usually it's time and money. It's too expensive, or it would take too long to, study every item in a population. Other times, whatever you're studying, you might have to destroy it in order to do the study. And that, again, comes back to money. And then other times you have populations that are essentially infinite. Study the number of water molecules on Earth. If you're studying that population, obviously it's essentially infinite, practically infinite. How do we do the sampling? You have your big population of interest, and then you want to study it by taking a subset. Now, there are many different sampling methods. We're just going to talk about a few here, and we'll talk about them, throughout the course. I just wanted to go over just the basics here. The simple random sample is the one we all know and love. Basically, put everyone's name in a hat and start drawing names. Everyone is equally likely to be chosen in that situation. I took my example from an old textbook, obviously. Randomly pick numbers from a phone book. What's a phone book? So some of these things are getting kind of dated. So that's probably the most common sampling procedure, is just random sample. It's very desirable. Other times we might have something that we want to do comparison with. If I want to compare the number of uh, men who believe that we should have more bike lanes in Vancouver to the number of women who think we should have more bike lanes in Vancouver, I might break the population into the strata of men and women and then take a sample of men and a sample of women uh, and then study those. So basically make some criteria to break the population down before doing the random sample. Other times we might look at systematic sampling. This is like in manufacturing. You can imagine on assembly line situations where items are on a conveyor belt, and you're not going to check every single item, but every 10th one or so, maybe take a look at it more carefully. And if it's okay, then you assume things are still going okay. And then as soon as you bump into one that isn't okay, maybe you go into further investigation. So that's a systematic way. It's in a way, random, but you've come up with a plan as to which item you're going to pick. Cluster sampling, this is where you break your population into entire clusters. This is kind of a nice visual of that. An airline company is interested in how people, feel about their flight, about various flights, rather than randomly selecting passengers, you know, which would be very difficult. I'd have to grab one passenger on flight 0649, another passenger on flight 9602. Uh, that might be costly and difficult, where it might be easier to just randomly pick a plane and test everyone on that plane, and then randomly pick a different one and check everyone on that plane. And that way, you still get a general overall feel of how people feel about your service, for example, without necessarily having to get, one person on or a couple people on each flight. Other sampling, maybe the worst one is maybe a convenience sample where you just use data that already exists, or you just select data. You want to know something about people's opinion, and you just contact your 5 best friends and ask them what their opinion is. Now, this doesn't give very reliable data. It isn't very random, but it's better than, say, no data at all, perhaps. A lot of times you'll see on the news, for example, they'll have a news story about, oh, coffee drinkers uh, tend to live longer. And this data came from a Harvard study. And that, as soon as you hear Harvard study, you think, well, maybe they're a respected school, therefore that this must have some meaning. Uh, but it's very possible that in a lot of those cases that Harvard was studying something else. And they just happened to be asking people, are you a coffee drinker? And someone noticed that in their data that they made available, and then drew their own conclusion that there's a correlation between coffee and living long, and then this starts to make the news. But it wasn't what the study was designed to test for, so it was convenient that there was existing data, but that should just be a starting point where you'd create a controlled study. But yeah, again, convenient data or mining old data is a big problem in statistics, or it's not really a problem for statisticians so much. It's a problem that other people will tend to glom onto these things. Speaking of problems, we'll talk about errors here. Sampling error versus non-sampling error. Now, sampling error is just the difference between your sample result and the population value. An example of this is you wrote a final exam last year, and I want to know how you guys did on it. So rather than getting the results of the whole class, I talk to 20 of you, and I get the results of those 20 students. I could get the mean of those 20 students, and I would hope that that mean would be representative of the whole population. Now, it wouldn't probably match. It certainly wouldn't match exactly. So there's a difference between our sample value and the actual value, and that's what this sampling error is. It's not really that you've made an error, it's just the difference between your sample value and your population. Actual errors are called non-sampling errors, and this is the case where you actually make a mistake. You write down a number wrong, or you posed the question in a biased way, or you didn't have a sample that represented the population at all. A lot of times when I'm in the classroom, I'll sample the front row of the class. What did you guys think about the midterm last week? And the front row will all say, oh yeah, it was great. Super fair, just the right length. Yeah, not bad at all. But in that sort of situation, we all know that, who sits in that front row of a classroom. That doesn't necessarily represent the whole class in general. So I've introduced bias in that situation. So we're going to be on the lookout now for these non-sampling errors. One, so that when we're criticizing someone else's work, we can be critical, and two, so that we can avoid making mistakes ourselves. So yeah, those are the main intro definitions. Now we'll talk about the branches of stats. In this course, we will talk about basic descriptive stats. We'll do some probability. We'll hit inferential statistics, and then we'll also do some other branches or kind of offshoots as well. But these are the main topics in statistics. So descriptive statistics is where we do the summarizing and data collection. And there's a lot to this. Like a lot of it seems like common sense, but there's still a lot of room for errors and problems. So we'll cover this in a fair bit of detail. Then we move on to probability. Basically, what are the percent chance that events occur? We'll come up with a few different ways to do these calculations. We'll learn some basic counting techniques. And then we'll move into, we'll basically put these two things together so that we can make decisions. That's what inferential statistics is all about. Basically, it's putting the plus or minus on your number. I'm 90% sure that a student will pass the course, plus or minus 3%. We can quantify my prediction, and we'll use that using probability. The other topics they're just sort of a mixture of these things. We'll talk about reliability. That's a nice probability application. Quality control. That's a descriptive statistics topic. It's all about sampling and looking at data over time. And then curve fitting is the method of least squares, basically adding trend lines to data as an example. So basically, we'll study these things, not exactly in this order. These middle topics kind of get scattered throughout the course. So we'll start with descriptive statistics. So descriptive statistics is that how do we collect data and how do we summarize it? And first we'll look at graphical summaries of the data, and then we'll move to numerical. So in your first couple of labs, you'll be doing some graphical things in Excel. So we do a few here in the lecture, and then you do a few more as Excel tutorials. So here are some graphical, some basic charts. The Pareto chart, which is a sorted bar chart. You'll do that in your labs. Uh, Pie charts, looking at percentages of uh, the distribution of various categories. Frequency histograms. Basically, it's like a bar chart, but with numeric values on the x-axis. We'll do examples of these. Ogive, which is a cumulative plot. Stem and leaf plots, scatter plots, control charts, and which are just special run charts, like basically data over time. A lot of times in statistics courses, the intro stats courses kind of are light on looking at data over time or looking for trends in that way. But it is an important topic, so we'll make sure that we scatter that throughout too. I thought I'd start out in the lecture notes here talking about stem and leaf plots, and it's hard to describe what they are or how to do them. It's a lot easier to actually just show you. So let's do a little example of a stem and leaf plot. So we'll make up some data here. We have Namzor Enterprises. They're interested in the amount of time it takes to build these manufactured trusses for roof rafters. And we have assembly times. We randomly picked 15 assemblies and we timed them. So the first one took 95 minutes. The next one took 81 minutes. The next one took 98 minutes at 15 values. When you just look at data like this, it's kind of hard to get much information out of it when you just are writing values down that you've collected. It's nice to come up with some way to summarize it where you might be able to find what the typical result is. Or you might want to identify, are any of these values unusually large or unusually small? And this stem and leaf plot will help us do that. Basically, what I did is I noticed that the values ranged from the 80s up to the 160s. So I made stems. That's why it's called a stem and leaf plot. You have our stems 80s, 90s, 100s, 110s, 120s, 30s, 140s, 150s, and then I can represent the leaves as the ones digit. So for this first number 95, I have my 90s category, and I just put a 5 there. And then I have my next value that I collected was 81, so I put a 1 there. And then 98, and then 128. And you just keep doing that. 101 until you have them all done. So 96, 4. I'll shut up. Here's 100. Remember to put a 0 for that one. 169 and 119 goes there. Now we have this data sort of summarized, and now some things stand out. We can see that a couple of those assembly times were pretty long. We can also get an idea of the shape of the data. Basically, we've created a histogram for this data. A very crude one. Basically, turn this thing on its side, and then certainly you'd have a nice little bar chart. It's actually a histogram because we have this numeric ranges on this axis. I wouldn't recommend putting this sort of chart in a research paper that you're writing, but if you're out in the field collecting data and you're jotting these things down in your notebook, now having a way, you could quickly sketch this thing out and have a rough idea of how things are going. before you've done any formal analysis. So a stem and leaf plot is not the most professional looking plot, but it does give you a quick way to look at your data. Something jumped out at us. Why did it take so long for two of those to be built? Should we fire somebody? Should we train someone? What is there an issue that we can correct? We can see the average amount of time is kind of in the 90s. So for a small data set, this is kind of a convenient way of summarizing data. We get to see roughly where the middle is. We get to see roughly the shape of the data. And we get to see how spread out it is and if there are any extreme values. So for such a dumb or crude graph, it does actually tell us a lot. What happens though if you had, 500 values? Then these bars would get to be so long that this wouldn't be very useful anymore. So we'd have to come up with something else. An improvement on the stem and leaf plot is the frequency histogram. I have some data here. I have 80 values in no particular order. They are emissions from an industrial plant. So this is sulfur oxide emissions from some plant. They're in tons on 80 different randomly selected days. One day emissions were 15.8 tons. Some other day they were 21.6 tons. It's really hard to identify if there are any extreme values in here. It's hard to see what the average is. I don't know what the shape of this distribution is. So I want to summarize it by making similar to that stem and leaf plot. Basically, instead of having my categories go by 10, 20, 30, 40, I could have them I can break them down into anything I want, as long as they're all the same width. So I chose to make classes that range from 5 to 9, roughly. So 5 to 9, then 9 to 13, then 13 to 17, then 17 to 21. Basically, I decided that I would have categories that are 4 units wide. And I chose just a nice number to start with. I looked at the data and I noticed there were no values under 5, so I picked 5 as my starting point. And I don't know why I didn't make them 5 units wide, and I made them 4 units wide, just to prove that I could, I guess, even though it would have been nicer maybe to have each class 5 units wide for readability. But I did conform to some rules. I made sure that each one of these classes was, 4 units wide, actually 4.9 units, 3.9 units wide, I should say. I did that to make sure that they never overlapped. I didn't want to ever have a value where I wasn't sure where to put it. Like, does it belong to this class or does it belong to that class? So I've gone to 1 decimal place and I made sure that there is no overlap. So I set my lower class limit as a nice number, and then I just went up to 0.1 less than. To create this frequency table, I basically scan through the list and I count how many of them are between 5 and 8.9. So I look through the list and I go, oh geez, here's one. Maybe I should use a different color here. There's one, and I should have looked at this ahead of time. 7.7 is one, and oh geez, there's the third one. So there were 3 in that category, and now I have to do that for all the rest. Now hopefully we can use computer software to do all this for us. It will basically do these counts. If we add all these frequencies together, we better equal 80, because that's how many values we have up here. So that's a good way to check. After we make a frequency table, this turns into a very nice plot. You put the class limits on the x-axis and you put your frequencies on the y-axis. Make sure that you start at 0 whenever possible so that you don't distort the data. And then we just plot these things as a bar chart. Notice how I don't have any gaps between the categories. That because there are no gaps between these. Every value should be in one of the categories. So I shouldn't see, big spaces between these, because that would make my eye believe that there's a category that has nothing in it, for example. The title of this plot is terrible. Frequency histogram is not a good title. When someone looks at your plot, it should kind of tell them, a lot more about this. What is this? Saying more in the title is better than not saying enough. So saying that this is daily emissions from Paul's industrial plant on 80 days in a particular year would be a better title than just saying frequency histogram. We want to label the other axes. I did an okay job there. I have daily sulfur oxide emissions, and I put units. So that's good. And the y-axis will always just be frequency, so that's not so bad. Look at this plot now. What do we see? We see that it has a nice shape. This is basically what everyone calls the bell curve, the normal shape, where most of your data is clumped up in the middle, and then you don't have very many values in the high end or the low end. Heights of adults in Canada probably have a similar distribution, where most people are sort of a typical height, and then there aren't very many that are super tall, and there aren't very many that are super short. This shape occurs a lot, and just naturally. So we'll be talking about this shape all throughout the course. I just thought I'd mention it now, the bell curve or normal curve. So yeah, we get to see the shape from this. We can quickly spot where the middle is, and we can see if there are any, obvious strange values. Like, had there been a bar way up here, that'd be unusual, and we could identify these, and maybe there are problems in some way. We also can see the last attribute of this chart we see is how spread out values are. Are these values clumped pretty close to, 18, or is it pretty easy to be far from the middle? So we'll talk about that too when we get into the numeric measures of how to measure how spread out values are relative to their mean. I converted this chart that we just did. I should mention before I go any further there, I said that I made my class limits 4 units wide. Why did I choose that? You might ask. And basically on a whim. I could have made them 5 units wide or 10 units wide. With computer software, I tend to just kind of fiddle around with it until I get a plot that looks good. Had I made my categories 40 units wide, 5 to 40, and then 41 to 80, it would be a pretty boring chart. You'd have two rectangles. So you wouldn't see very much. So you want to make sure you have enough categories that you can actually, represent the data, but not too many categories that you just end up with a straight line. So there's you kind of tweak it until you get what looks nice. One way to do it is maybe to find the maximum value in your data set. The highest value in here is like 32, and the lowest value in the data set was like 6. So you could take the difference between the highest value and the lowest value, and then divide it by a nice number like 10 or 5 or 7, and that would tell you how wide to make each category. That's a good starting point for that. But really, it's something that's a bit of an art. You play around with that width of the category until you get one that you're satisfied with. I took the table that we had on the previous example. We had our frequency table, and here are those same frequencies. And rather than plotting the frequencies, I converted them to percent. This gives us a relative frequency histogram. We had 80 values in our data set, so I just divided each of these by 80 to get the following results. Hopefully, if you add up this column, you get 100%. And I created the plot using percent on my y-axis instead of frequency. You'll see it's the exact same picture that we had in the previous one. You still get the same shape. You still see the middle. You can still kind of gauge how spread out values are and if there are any outlying values. The advantage of using relative frequency over frequency is it allows for comparison a bit easier. If I had to compare, suppose this data was all collected 5 years ago, and now I want to compare it to what's going on this year. But this year, I didn't collect as much data. Maybe I only did samples on 40 different days. Well, it would be hard to compare the two plots that I'd create if one of them has 80 values in total and the other one has 40. But if I convert them both to percentages, then I can more, fairly compare them. So oftentimes I prefer the relative frequency histogram over the just traditional frequency histogram. We have cumulative charts where we take our frequencies, and remember our first frequency was 3 in the first class, and then the next one was 10. Well, I added those two values together to get a cumulative amount. And then the next category had 14 in it. I'll just scroll back for a second so you can see. The first category has 3. Then in the second category, it's 10 plus the previous 3, which is 13. And then the next one would be 14 plus the previous 13, which is 27. And you just keep doing that until we'd hit the last category, which would have a cumulative total of 80. And that's what I did in this chart here. We can either look at the raw totals, or again, we could look at them in terms of percentages. And then we can make a plot comparing the class versus the cumulative amount. Instead of putting a range of values, up above, we had class limits, which were a range. We had 3 values between 5 and 8.9. So I know that 3 values are smaller than or equal to 8.9. To make sure that I don't ever have to worry about less than or equal to, the tie situations, I basically went to a class boundary. I went halfway in between the two categories. So the first class ended at 8.9 and the next one started at 9.0. So halfway in between is 8.95. I can say 3 values are smaller than 8.95 and 13 values are smaller than 12.95. By adding an extra decimal place, I make sure that I never have any values that I couldn't figure out which category to put them in. So once we have this, we can make a nice plot. The plot has a fancy name. It's called an ogive. Basically, I put these class boundaries on the x-axis, and I put the cumulative frequency. I basically am plotting this column, although I could have done the percentages as well. But in the example I've given here, I just used the frequencies. And you'll always get something that continues to trend until you hit your total. Or if it's in percentage, the last one will always be 100%. What might we use this sort of plot for? Well, you can gauge the data based on how steep it climbs. You can do basic interpolation. An example might be, how many days were emissions less than 15 tons? Well, I can go to my chart here, and I can go to, 15 tons, and I can see that it's about, 20 days. Even though I don't have a data point for that, I can come up with a reasonable interpolation as long as I'm between. I wouldn't want to, go beyond the data set necessarily to make predictions, but I can at least predict within the data that I have. So these are some of the graphical things that we've done, or that we will use to summarize data, and you're going to do more in your labs. So I think what we'll do is we'll call it here for this first video, and we'll carry on with these topics in the next one. But I didn't want to have these things super long, although I'm sure this felt pretty long. Anyway, I will see you all in the next one. Take care.